Good day, everyone! This is Charmive Bagandol from 3rd year Bachelor of Science in Marine Biology, and this is a continuation video report presentation of Chapter 5, Geometric Designs. In this episode, we will determine how to analyze geometric shapes according to the level of geometric thinking. First, we have Peer Van Heel, Theory of Geometric Thinking, or simply the Van Heel Model. This theory describes how young people or students learn geometry. The Van Heel model contains 5 levels: visualization, analysis, abstraction, deduction, and rigor. Each level introduces its own concepts, symbols, and language. At this level, the shapes become bearers of their properties. The objects of thought are classes of shapes, which the student has learned to analyze as having properties. For example, a person at this level might say, a square has 4 equal sides and 4 equal angles. Its diagonals are congruent and perpendicular, and they bisect each other. The properties are more important than the appearance of the shape. If a figure is sketched on the blackboard and the teacher claims it is intended to have congruent sides and angles, the students accept that it is a square, even if it is poorly drawn. Properties are not yet ordered at this level. Another example, they will still insist that a square is not a rectangle. They may introduce extraneous properties to support such beliefs, such as defining a rectangle as a shape with one pair of sides longer than the other pair of sides. Students begin to notice many properties of shapes, but do not see the relationships between the properties. Hence, they cannot reduce the list of properties to a concise definition with necessary and sufficient conditions. They usually reason inductively from several examples, but cannot yet reason deductively because they do not understand how the properties of shapes are related. In abstraction level, properties are ordered. First, students perceive relationships between properties and figures, creates meaningful definitions, able to give simple arguments to justify their reasoning, can draw logical maps and diagrams, use sketches, grid paper, geometric software, recognizes the importance of properties and the relationships among them, which assist students in logically ordering the properties of the shapes. The student then understands that properties are related and one set of properties may imply another property. Students can also reason with simple arguments about geometric figures. A student at this level might say, isosceles triangles are symmetric, so their base angles must be equal. Learners recognize the relationships between types of shapes. However, they do not yet understand the intrinsic meaning of deduction. They cannot follow a complex argument, understand the place of definitions, or grasp the need for actions, so they cannot yet understand the role of formal geometric proofs. Next is Level 3, Deduction. Students can give deductive geometric proofs, able to differentiate between necessary and sufficient conditions, identify which properties are implied by others, understand the role of definitions, theorems, actions, and proofs, attains logical reasoning ability, proves theorems deductively. Moreover, students at this level understand the meaning of deduction. The object of thought is deductive reasoning or simple proofs, which the student learns to combine to form a system of formal proofs, or the Euclidean geometry. Learners can construct geometric proofs at a secondary school level and understand their meaning. They understand the rule of undefined terms, definitions, actions, and theorems in the Euclidean geometry. However, students at this level believe that axioms and definitions are fixed rather than arbitrary. so they cannot yet conceive of non-Euclidean geometry. Geometric ideas are still understood as objects in the Euclidean plane. Lastly, Level 4, Rigor. At this level, geometry is understood at the level of a mathematician. Students understand the way mathematical systems are established, can comprehend between Euclidean and non-Euclidean geometry, able to describe the effect of adding or removing an axiom on a given geometric system, can establish and analyze theorems in different postulation systems. The object of thought is deductive geometric systems, for which the learner compares axiomatic systems. Learners can study non-Euclidean geometries with understanding. People can understand the discipline of geometry and how it differs philosophically from non-mathematical studies. Moving on, the Van Heel levels have 5 properties. First is the fixed sequence. Second is the adjacency. Third, distinction. Fourth, separation. And lastly, attainment. In fixed sequence, the levels are hierarchical. Students cannot skip a level. The Van Heels claim that much of the difficulty experienced by geometry students is due to being taught at the deduction level when they have not yet achieved the abstraction level. Next is adjacency. Properties which are intrinsic at one level becomes intrinsic at the next, or at each level, what was intrinsic in the preceding level becomes extrinsic in the current level, which means that the properties are there at the visualization level, but the student is not yet consciously aware of them until the analysis level. Properties are in fact related at the analysis level, but students are not yet explicitly aware of the relationships. Next is distinction. What may be correct at one level is not necessarily correct at another level, because each level has its own linguistic symbols and network of relationships. The meaning of a linguistic symbol is more than its explicit definition. It includes the experiences the speaker associates with a given symbol. At level 0, a square is something that looks like a box, and at level 2, a square is a special type of rectangle. Neither of these is a correct description of the meaning of square for someone reasoning at level 1. If the student is simply handed the definition and its associated properties without being allowed to develop meaningful experiences with the concept, the student will not be able to apply this knowledge beyond the situations used in the lesson. Okay. Next is separation. Two persons at different levels cannot understand each other. A teacher who is reasoning at one level speaks a different language from a student at a lower level, preventing understanding. For example, when a teacher speaks of a square, she or he means a special type of rectangle. A student at level 0 or 1 will not have the same understanding of this term. The student does not understand the teacher, and the teacher does not understand how the student is reasoning, frequently concluding that the student's answers are simply wrong. The Van Heels believed this property was one of the main reasons for failure in geometry. Teachers believe they are expressing themselves clearly and logically, but their level 3 or 4 reasoning is not understandable to students at lower levels, nor the teachers understand their students' thought processes. Ideally, the teacher and students need shared experiences behind their language. For the last one, attainment has 5 phases: the information, guided orientation, explanation, free orientation, and integration, which are approximately not strictly sequential. In the information or inquiry, students get acquainted with the material and begin to discover its structure. Teachers present a new idea and allow the students to work with the new concept. By having students experience the structure of the new concept in a similar way, they can have meaningful conversations about it. For example, a teacher might say, "This is a rhombus. Construct some more rhombi on your paper." Next, the guided or directed orientation. Students do tasks that enable them to explore implicit relationships. Teachers propose activities of a fairly guided nature that allow students to become familiar with the properties of the new concept which the teacher desires them to learn. For example, a teacher might ask, "What happens when you cut out and fold the rhombus along a diagonal, the other diagonal, and so on?" followed by discussion. In explanation or explicitation, students express what they have discovered and vocabulary is introduced. The students' experiences are linked to shared linguistic symbols. The Van Hills believe it is more profitable to learn vocabulary after students have had an opportunity to become familiar with the concept. The discoveries are made as explicit as possible. For example, a teacher might say, "Here are the properties we have noticed and some associated vocabulary for the things you discovered. Let's discuss what these mean." In free orientation, students do more complex tasks, enabling them to master the network of relationships in the material. They know the properties being studied, but need to develop fluency in navigating the network of relationships in various situations. This type of activity is much more open-ended than the guided orientation. These tasks will not have set procedures for solving them. Problems may be more complex and require more free exploration to find solutions. For example, a teacher might say, "How could you construct a rhombus given only two of its sides?" and other problems for which students have not learned a fixed procedure. The last one is integration. Students summarize what they have learned and commit it to memory. The teacher may give the students an overview of everything they have learned. It is important that the teacher not present any new material during this phase, but only a summary of what has already been learned. The teacher might also give an assignment to remember the principles and vocabulary learned for future work, possibly through further exercises. For example, a teacher might say, "Here is a summary of what we have learned. Write this in your notebook and do these exercises for homework." Supporters of the Van Hill model point out that traditional instruction often involves only this last phase, which explains why students do not master the material. So, I guess that would be all for this video report. Thank you for watching. Always remember, just enjoy and trust the process of learning.